Operation Classroom. Here we are going to discuss equilibrium determination of equilibrium constant from Gibbs free energy of formation for this reaction of methanol formation. Uh, so, my name is Shekhar Bhattacharjee. Methanol is formed by the following gas phase reaction here. Carbon monoxide reacts with hydrogen in the gaseous phase to form methanol. The standard Gibbs free energy of formation are given for carbon monoxide and methanol, and we'll see why hydrogen is not given. The value of the R is given. So equilibrium constant will be at 298 K, that this value has to be calculated and times 10 to the power 4. So that's here the value comes in. Here is a schematic and thermodynamic data for this problem is shown here. So let's say this is my reactor. We'll make an ideal gas assumptions. So the reactants are entering here, and then the product methanol is coming out from here. So this is a gas phase reaction at 298 K. That gives energy of formation of carbon monoxide and methanol are given, and the gives energy of formation of hydrogen and any other the permanent gases like nitrogen, oxygen, etc. These are assumed to be zero at standard state. Just refer to any particular standard textbooks, and that will tell you why. And of course, this is the standard equation for calculating the value of equilibrium constant at a certain temperature from the Gibbs energy of formation, which is of course at 298 Kelvin and 1 bar pressure. Let's see how we do the calculations here. So we're calculating the standard Gibbs energy of formation for this reaction here. So the standard Gibbs energy of reaction at 298 Kelvin and 1 bar is given by this equation here, which basically this nu are the stoichiometric coefficients, and these are of course the Gibbs energy of formation at standard state. This is the standard state. And remember, this stoichiometric coefficients are positive for products and negative for reactants. So if I simplify this one right here, so we can say this is equal to this. That means we do the for products. Minus, of course, the Gibbs energy of formation for each reactant multiplied by the corresponding stoichiometric coefficients, and both of them at that standard state. So once we substitute this values, given this value for hydrogen, we say this is going to be equal to 0. For hydrogen, this is going to be 0. This is given. So this calculations is shown. So this comes out to be negative of 25 kilojoule per mole. All right. So next, we calculate the equilibrium constant. So this is again a very standard equation here. So the value of the equilibrium constant at 298 Kelvin is given by this one right here. That's a negative of Gibbs energy of reaction at standard state. Remember, at standard state, this is also at standard state same. And RT, the value of R is given. T, of course, is 298 Kelvin. And K is, of course, where we know is the activity ratios, of course, raised to the corresponding stoichiometric coefficients for this reaction here. So the detailed calculations are shown over here. And if you calculate the value of K, this becomes 2.41 times 10 to the power 4. Since 10 to the power 4 is already given in this equation, so the answer should be equal to 2.41, which is right here. So this value would be 2.41. That's the answer. And one thing must be mentioned that although for such a large value here, although methanol formation is thermodynamically favored, that means along this direction here, at 298 Kelvin, the reaction rate, since the temperature is very low, almost room temperature, the reaction rate is extremely low. Commercial methanol synthesis is carried out at a much higher temperature, around this temperature and about this pressure. We'll see why using this particular catalyst, and there are several other catalysts, proprietary catalysts. And we'll discuss this in little more details later on. So, what are the key concepts and the learning outcome from this problem? First of all, to calculate the Gibbs energy of formation, we have to use this equation here that the Gibbs energy of reaction comes from the Gibbs energy of formation for each reactant and the product and the corresponding stoichiometric coefficient, where the stoichiometric coefficients are positive for products and negative for reactants. The second learning outcome is the standard free energy of formation of an element in its standard state, as for example, like hydrogen, oxygen, nitrogen, permanent gases, is defined as zero. Please see a standard textbook. Please see a standard textbook for your lecture notes. Negative value of the heat of Gibbs energy of reaction at standard state indicates that the forward reaction is thermodynamically favorable. Forward reaction is thermodynamically favorable under standard condition. Is thermodynamically favorable. We'll see what meant by this favor, thermodynamically favorable. So let us now interpret the values of delta G and K is what the values what we have got. The equilibrium constant is obtained directly from this equation. We have seen we have calculated the value of K, which is equal to 2.41 times 10 to the power 4. And where the value of K is just was the activities and raised to the power corresponding stoichiometric coefficients here. In general, when the standard Gibbs energy of reaction is negative, less than zero, it gives a value of K greater than 1. And the product formation, that means the forward reaction is favored, thermodynamically favored. So this reaction is favored. When the Gibbs energy of reaction is positive, that of course gives a value of K less than 1, where of course, as you can see here from this reaction quotient, that the activities of this one is much less than this one, going to be this one right here. So the forward reaction is not favored. So this forward reaction is not favored. So that does not mean that the react products are not. The products are still formed. Okay, but of course this is much less quantity, and the exact equilibrium composition of course depends upon the temperature, pressure, and the feed composition, and of course on the stoichiometry. If let's say that the heat reaction, standard Gibbs energy of reaction is equal to 0, that of course will give a value of K is equal to 1. This is the natural log. So neither side is favored. So let's say if we have a hypothetically reaction A is going to be converted to B in equilibrium, then of course activity of A is going to be activity of B if this delta G of reaction is equal to 0. That normally not happens. Now let's look at the practical interpretation of K. So as we said, if the standard Gibbs energy reaction is negative, K is going to be greater than 1. Product side activity is large, so the forward reaction is favored. If delta G reaction is greater than 0, then of course the K value is going to be less than 1. And then the reactor side activity ratio determinant. That doesn't mean the products are still formed. Okay. And if this is approximately 0, K is going to be equal to 1, and both side activity ratios are appreciably presented in the equilibrium composition. We just use a practical rule. This is a thumb rule, approximate rule, so don't rely on it. If K is approximately greater than 10, then they're thermodynamically favorable. If is in the range between 0.1 and 10, this is potentially feasible for industrial application with suitable process design. If K less than 1.1, this normally, but if the other parameters are favorable, we'll see why, normally requires equilibrium shifting measures. We'll see. These are all given standard textbooks or consult your lecture notes. Let's just spend a minute on thermodynamics, kinetics, and catalysis because these are very interrelated. Number one, the equilibrium constant is always dimensionless. We have seen that from this equation here. The equilibrium constant is going to be, of course, the equilibrium constant is, of course, always going to be dimensionless. A large K does not guarantee a rapid reaction. Large K value says that the products are appreciated form, so that the equilibrium composition, the product composition is going to be very high, product concentration is going to be very high. But it does not say this is going to be a rapid reaction from the start to finish. Okay, that is the domain of kinetics. For a specified heat composition, thermodynamics predicts the final equilibrium composition at a fixed. So if you fix the temperature and pressure, it tells you what is the final equilibrium composition is going to be. But how fast it's going from the very start of the reaction to here, it may take even few seconds, it may take few days. So that depends on the kinetic parameters. A catalyst does not, in kinetics determines how quickly equilibrium is approached. So that is given by kinetics. A catalyst does not change K or equilibrium composition for the same feed at a fixed temperature and pressure. It only enables equilibrium to be approached with rapidly. So if we remember here, so it goes to some active state here. So if you use a catalyst, so this activation and load equals load activation, but the final equilibrium composition does not change. Now let us discuss making equilibrium constant limited process feasible. These are very standard industry procedures. So just going to give you some basic rules. A reaction with K less than 1 can also be industrially feasible if other parameters, let's say economics dictates it. So let's see. So these are basically equilibrium limited processes. You can use recycle, where of course we after the reactor we separate the reactants from the products, and the products are maybe condensed and cooled, and the reactants are of course sent back, right? So the recycle. But remember, in recycle, past conversion may be low, but recycling increases the overall conversion. But recycling does not shift equilibrium, does not change the value of K. Using one reactant in excess increases conversion of limiting reactant by changing the reaction quotient. Remember the activity ratio, the raised to the stoichiometric coefficient. Let's say for this one, if we feed here, let's say it is equilibrium limited, but if we feed excess of B, it will increase equilibrium conversion of A. Continuous product removal reduces reaction quotient and drives further forward reaction, let's say by condensation or separation in a distillation column or by extraction. Let us spend a minute on effect of temperature on K. We know the equilibrium constant is, so we have seen how to calculate the value of equilibrium constant to 98 K. From this particular value, you can calculate the value of K at any other temperature. So this is the way you calculate the value to 98 K. The value of K, of course, varies with temperature. Pressure affects pressure affects in a different way. But these are values of K which are function of T only. Okay. So KT at any other temperature is calculated using Van 't Hoff's equation. This is a very standard one, where of course this is assumed to be constant. So these are given in a standard textbook. Okay. If this is we know that heat of reaction is as a function of temperature. In that case, of course, we use this equation here to calculate the value of K2 at this would be at 298. We have seen how to calculate this from the standard Gibbs formation. To calculate the value of K at any other temperature, pressure we will see later. At any other temperature, we can use this one. Of course, these are given in a standard textbook. We'll just quickly look into the industrial methanol process, how it's produced from syngas. First, of course, the syngas production. We have discussed it in several other places. From natural gas reforming, we can get that. From coal gasification, biomass gasification, green hydrogen, carbon monoxide, carbon dioxide. So that's the way, of course, we get the syngas. Once we get the syngas, we compress it, and then we send it to the catalytic methanol synthesis reactants. Let's say this is a typical catalyst here. This is the typical reaction conditions, temperature and pressure, and this is an exothermic, so it needs an efficient heat removal process, like say using a steam boiler. So then, of course, the products are cooled and condensed, and that's the gas liquid separated here. And of course, we get cooled methanol product, and what are the unreacted gases? That's are, of course, reactants that are sent back. And of course, as a recycle, and of course, we have to take out the parts because there will be some amount of, otherwise there will be some amount of inert buildup. So there has to be a part stream. Again, look into some standard textbook on the technology of why you use purge and how you use that in a recycle. Industrial production of methanol from syngas. How is it? What is syngas, by the way? It's a mixture of carbon monoxide, carbon dioxide, and hydrogen. Okay. Natural gas from we get it from natural gas reforming. It's approximately 70% hydrogen, 15% carbon monoxide, 10 to 13% of carbon dioxide. Balance might be methane and inert gases. So this is the reaction way here. So methane, this is a steam methane reforming where we get carbon monoxide and hydrogen. This is a strongly endothermic reaction carried out at a high temperature reformer in a furnace. So we have seen that in other problems. And there's an accompanying water gas shift reaction where carbon monoxide react with steam to produce carbon dioxide and more hydrogen. So the overall reaction is this. Okay, again, look at substandard textbooks. What's the effect of pressure? We have discussed the effect of temperature, but let's see what's the effect of pressure. Let's say for this particular reaction, you can see the difference, of course, of the stoichiometric coefficient is equal to 1, -1, -2. So that's what it is over here. So the economic constant, which is, of course, the reaction quotient is given by this is the ratio of fugacity and the fugacity at standard state. And if we make an ideal gas assumption, then this is what it comes to. So as you can see that for methanol formation reaction, higher pressure increases the equilibrium methanol conversion. So basically, so if we have a higher pressure, then of course it will increase the ethanol, higher methanol conversion. So important, temperature changes the value of K. So we have seen how temperature changes the value of K, and we can calculate that from Van 't Hoff's equation. Pressure changes equilibrium composition, but not K. Pressure changes equilibrium composition according to this particular reaction in a way. Of course, for different reactions, these numbers would be different. These quotients would be different. Difference in this would be different. So you have to formulate that. But as I said, temperature changes K, which is from Van 't Hoff's equation, but pressure change you have to find out this particular way. Okay. Effect of temperature on equilibrium conversion for methanol formation. So these are the two reactions we have seen for methanol formation. So if let's say carbon monoxide and carbon dioxide, which are both present in syngas, can produce methanol depending on the catalyst. So Van 't Hoff's equation used to calculate the effect of temperature. So as you can see, so this is an exothermic reaction, so that's negative. So this is negative at a fixed pressure and fit composition. Equilibrium conversion of methanol decreases with rising temperature. So let's say if you even use Le Chatelier's principle, we know you can assume that heat generated is as a product. So you can there's a heat generated is a product. If you assume that, then you can say as the temperature will rise, it will shift equilibrium towards the reactants, right? So we'll try to avoid, since there's an exothermic reaction, higher temperature will reduce the equilibrium conversion. So what is the trade-off? Equilibrium conversion, maximum thermodynamically possible conversion decreases, which is the equilibrium conversion, decreases continuously as temperature increases. We have seen here. At the end, but if we go at a lower temperature, let's say room temperature, the value of K is very high. Large value of K indicates equilibrium. Remember that's around 2.4 times 10 to the power 4. It's a very high value. So that favors methanol formation, but the reaction rate for such low temperature, because this depends on the exponential dependence of temperature. Reaction kinetics on temperature. We can look into the Arrhenius equation. So at this condition, the equilibrium conversion may be high, but the kinetics is very low. At moderate temperatures, around this one, the reaction rate is reasonably high. The equilibrium conversion is acceptable, preferred desalinate, and conversion to methanol is acceptable. So this is what is. So this is a trade-off. So that's how in industry the reactors are designed. At higher temperatures, of course, intrinsic reaction is greater, but equilibrium constant and the maximum attainable methanol conversion will work. Plus, of course, there are limitations on the material construction of the reactor. Why high temperatures avoided? Very high temperatures are avoided because equilibrium methanol yield decreases with increasing temperature by product formation. But byproduct formation increases and catalyst sintering and deactivation. Okay. So basically what we say that at lower temperatures, it is kinetically limited. Kinetics is very low. At higher temperatures, equilibrium limited, because equilibrium conversion, since this is an exothermic reaction. The reactor must be designed and operated at an optimum temperature. And requires also, of course, efficient heat removal system because this is an exothermic reaction. So what are the practical engineering design rules? K is an important thermodynamic screening parameter, what we have seen. Process design of commercial reactors depend on thermodynamic equilibrium, temperature, pressure, and equilibrium composition, kinetics, catalyst activity and stability, selectivity, recycle, condensation, separation. As for example, removing water during esterification process, condensing ammonia, methanol, removing hydrogen using a membrane process, precipitating solid, etc., etc. That's how the product is removed, and we drive the reaction towards the forward reaction. Okay, so finally, with all this information, just let's go back to the basic initial problem. We have seen how the problem is solved, and that, of course, is 2.4 is the correct answer, what we have seen here, 2.41.